So in Module 8, we'll talk about common statistical tests. And the basis of this is, previously we talked about developing hypotheses that can then be investigated using data. And a starting point is obviously to explore the data. So we might create table summaries, we might create graphs or charts. But really what we're hopefully trying to get to is empirically testing if what we observe or what we believe to be the case, maybe based on these tables, charts, or graphs, is actually significant. In this case, we're talking about statistical significance. So we use statistical tests, and there's a number of common tests that are used to test various hypotheses. And I mentioned before that the tests that you can use is based on the type of data that you have, right? Is it numeric? Is it categorical? What gets a little bit more complicated because, in fact, when we think about statistical tests, there's actually parametric tests which assume a distribution, and then there's non-parametric tests where there's no assumption about the distribution of the data. And then you can see there that, in fact, with parametric tests, that's used for numeric data or continuous numeric data. And with non-parametric, we can work with actually ordinal, nominal, and actually skewed numeric data. Oftentimes with parametric, we might be testing averages, right? So testing the difference between averages, whereas non-parametric, we can look at medians, ranks, or distributions. With parametric, they're more impactful with larger data sets. With non-parametric, we can actually work with smaller samples or smaller data sets or non-normal data. And you can see some examples there, but the idea is that when you think about a parametric test and then you maybe violate that assumption around the normal distribution, there's going to be an equivalent non-parametric test. And the final point there is the use case, right? So the parametric we're using when data meets this normality assumption. Often we're looking at the variance as well. With non-parametric, we'll more so use when the data is skewed, ordinal, or has outliers. And then when we think about this, we want to make sure that we're actually testing these assumptions, so we're not blindly applying a parametric test when in fact we should use a non-parametric test. So let's talk about hypothesis testing. Ultimately, all these tests, there's a null hypothesis and an alternative hypothesis. So with the null hypothesis, we were assuming basically there's no effect or no difference or no relationship of some kind. Alternatively, this is going to, the alternative hypothesis, we're going to contradict that null, right? So we're going to suggest that there is a significant effect or a significant difference or a significant relationship. And it's just, as a note, it's actually important to understand for each test what the null actually is testing and what the alternative is, right? Because it can vary from test to test because we're working with different data types and different variables. So often we look at what's referred to as a p-value to assess statistical significance. So a p-value we can think of as a probability that tells us how likely we are to observe the results we got. So how likely we are to observe the results we got if the null hypothesis were true. Another way of saying this, it actually helps us decide whether an observed difference is meaningful or just due to chance. So the smaller that probability value is, the more confident we can be that we're not making a mistake by, for example, rejecting that null hypothesis. So you think about an example with startups. If we're analyzing startups in the tech industry and we're trying to understand whether startups in tech are more likely to get funded than those in other industries, we might have a null hypothesis where industry type has no effect on whether the startup gets funded. Alternatively, it does influence funding. And you might run a test. In that case, it's what we refer to as a chi-square test because we have categorical data, right? Categorical and categorical, right? So industry is categorical. Whether or not a startup gets funded is categorical, right? Yes, no. We get a p-value of 0.03 or 3%. For social sciences, we usually use the cutoff of 0.5. So in fact, in that case, we would reject the null hypothesis that industry type has no effect on whether a startup gets funded, and then suggest that the tech industry actually has a higher prevalence or higher likelihood of getting funded. With the common statistical tests, we have a dependent variable in mind, right, and then some independent variable, and we're going to test that relationship. So with a t-test, for example, our dependent variable is numeric. The independent will be categorical with two groups. So we're testing the difference between those groups for that dependent or numeric variable. And then with the chi-square test, we're looking at, as in the previous example, discuss demonstrated categorical and categorical. With ANOVA, another common test, the dependent is numeric and the independent is categorical, but more than two groups. And then finally, you see correlation there. And correlation is when we have two numeric variables, right? A numeric dependent variable and numeric independent variable. And I'll actually show you that we actually can evaluate or test some of these using our Shark Tank dataset, right? So let's take a look at some application and the visualization and the exploratory work we did earlier. We saw some initial relationships, and now we're actually going to formally test those. So I'm going to see here, you can go ahead and import some libraries that I'm going to need, and we're going to pull the data directly from Kaggle, right? So we showed that earlier in a previous module, and we'll let that load. And then we'll start running our statistical test, right? So you can see our data. I'm just printing the data again, and we can see all our variables here. So that's going to be important in knowing that with respect to the variable types. And we'll look at our first test here. So this is a t-test, and what we're trying to evaluate is there a statistically significant difference between the group that got a deal and the group that did not get a deal with respect to their valuation requested, right? So the dependent variable is the valuation, and then the independent variable is there a difference between those that got a deal and those that did not get a deal. So we're going to go ahead and run this. And if we look at our results, obviously we're comparing means. The mean for non-funded startups is about 3.5 8 million. The mean for funded startups is 3.4 million. And we have our p-value, and the p-value is 0.2817. You actually see a t-statistic here. This t-statistic goes hand in hand with this p-value. So you'll see different statistics that are associated with each test. But the p-value is kind of a global or universal way to evaluate statistical significance. We can also look at confidence intervals as well. But when we think about the p-value, we'll look at, is that p-value less than 0.05? And in this case, it is not. So we can't reject this null hypothesis. In other words, it doesn't appear that there's a statistically significant difference in the valuation requested for those that got a deal versus did not get a deal. Well, it turns out that that's a parametric test, and we want to check on our assumptions. And the t-test actually has a couple assumptions, and it might be good to familiarize yourself whenever you use the test. But we have this example here where we can look at the normality assumption. One other thing we want to test is homogeneity of variance. And when we think about the p-values, we can actually generate a t-test that assumes the variances are equal or does not assume that the variances are equal. In this case, we assume that they are not equal, right? Equal variances equals false. So we're going to check all these assumptions, but if we violate this normality assumption, it actually means that we have to use a different test. So we're going to evaluate these two assumptions and check out the distribution, and let's go ahead and run that. All right. So it appears now that you can see that this first test, Shapiro-Wilk, it's looking at normality, and if the p-value is less than 0.05, the data is not normal. So if we see this here, it does appear to be the case. If we look at that p-value for each of these, that the data is not normal, right? So you can actually see that when we put the distribution together visually. You can see funded and non-funded, and that obviously does not follow a normal curve. For Levine's, the p-value is 0.1044. If that p-value is less than 0.05, we would say the variances are not equal. And in that case, we would just look at that variation for the t-test. But that, of course, is assuming that we're passing this normality assumption. Well, because I know that we didn't actually pass this normality assumption, I actually have to use a different test or a non-parametric test. So when we think about this, we can look at, well, this is also just looking at the box plot as well, right? So you can see the distribution a little bit better actually in the histogram versus the box plot by group or by non-funded versus funded. But because we're not meeting this normality assumption to be able to use the t-test, we actually have to use a non-parametric alternative. And the non-parametric alternative is shown here, the Mann-Whitney U-test. So we can go ahead and run that, and it actually shows for us that the p-value is 0.45. So again, that p-value is not less than 0.05. So in fact, the results are consistent with the t-test or the parametric version. So in this case, we would still not reject that null hypothesis, that there's no difference between the average valuation for funded startups versus non-funded startups. So that's working with two groups, right? And we have that dependent numeric variable, which in this case was the valuation. If we go into categorical versus categorical, I mentioned we would use that chi-square test, right? So we might look at, similar to the example, industry and whether the startup got a deal or did not get a deal, to see if there's a relationship between them or between these variables. So what we're going to do is we're going to create a contingency table. We'll look at the frequencies, and then we'll actually see if what we observe in our data is different than what we would expect. And the expected counts are actually based on this idea that there is no relationship between these two variables, right? These two categorical variables. So we're going to compare what we'd expect if there isn't a relationship versus what we observe in the data. And we'll actually be able to do that pretty easily. So let's actually look at this. So in fact, our p-value is not less than 0.05, and we can see the actual counts and expected counts as well. So the actual counts and expected counts, and basically what we are looking for is, are there large differences between what we'd expect to see, right? Expect to see and what we observed. If you do see large discrepancies between these cells, it would suggest to us that there is a relationship between these variables, or they're not independent. If they're very similar, then we would basically be able to say that there is not a relationship between these two variables, right? And you can see here that they are, in fact, fairly close, and the differences are not large enough to trigger statistical significance. So with the chi-square here, you can basically infer that because our p-value is less than 0.05, or our p-value is not less than 0.05, in fact it's much larger, it's 0.4208. Because it's larger, that we can't suggest that there is a relationship between industry and whether or not the startup got a deal or received a deal. Okay, so that's our categorical, and then we can look at ANOVA. In this case, when we think about ANOVA, we're looking at, similar to the t-test, a numeric dependent variable, and then a categorical variable with more than two groups. So in this case, we're looking at the total deal amount and then industry. And obviously we saw earlier with the chi-square that there are many industries, in fact more than two. And so we're actually going to look at the ANOVA to see if there's a relationship between industry and total deal amount. So let's go ahead and run that. And in fact, when we look at that p-value there, and again I mentioned that there's a sort of corresponding stat to each test. In this case it's the f-stat or f-statistic. But if we look at that universal p-value, it is much lower than 0.05. It's basically 0. So that would suggest to us that there are differences across industries in terms of the deal amount, right, or investment amount. Well, okay, there's differences. We can see, automotive. This is the average deal amount, 420,000. Business services, 341,000, 218,000, 307. So obviously there are differences. But which of these pairs, in terms of industries, are different? And in this case, we actually have to do what's called a post hoc test to identify which of these pairs are statistically different. And if we look at this, we can actually look and use the Tukey's test, HSD test. And if we look at that, you can see that we're looking at a bunch of pairs. There's a lot going on here, but what I'm actually going to do is extract the significant results so we can print those and take a look. So if we extract just the significant ones, we'll see that we have a clear picture on the significant industry differences, right? So automotive and travel, business services and travel, children's education, health and wellness, right? And it actually shows us the average difference between these groups, right, or these pairs in terms of the deal amount. So that's how we would use sort of a variation here where we need to actually do a post hoc test, because at first we're just seeing, okay, there is a difference, but what are the differences, or where the differences actually lie? And that's where we need a post hoc test. So let's finally look at correlation. And there's a lot going on here, but we'll start with the fact that we are looking at deal valuation and total deal equity. So is there a correlation between those two variables? And there is still here a null hypothesis and alternative hypothesis. So if we consider that the null is there's no correlation, alternatively there is, right? So the null is there is no correlation, alternatively there is, and we'll actually be able to take a look at what's called the correlation coefficient. This ranges from -1 to 1. If it's close to 0, basically no relationship. If it's closer to -1, negative. Closer to +1, positive, right? So -1 and 1 are perfect correlation, or they move perfectly together in one direction or the other. Whereas in this case, you can see that we have a negative 0.4017, right, for that correlation coefficient. It does also produce a p-value, so we can reject the null here, right? There is a statistically significant correlation between valuation and equity offered, and it's negative, right? It's actually negative. And the way we interpret this, right, is as the deal valuation increases, the total deal equity decreases, right? Total deal equity decreases. So there's a negative relationship between these two variables. Well, in fact, there are some variations that we can look at for correlation. So we're going to look at Pearson, Spearman, and then Kendall's tau. So Kendall's tau is the non-parametric version. Pearson actually assumes a linear relationship, whereas Spearman actually assumes a monotonic relationship. So you can test those as well, just to confirm. And yeah, so we can see those guys there, right? So it's actually significant for all. The p-value is less than 0.05 or much lower. So significant regardless of what variation we use. We also might look at the doing like a log transform of the data. So there's a plot there as well. And that's really if we have nonlinearity present, which in this case doesn't really appear to be linear, right? So we can look at a log transform as well and take a look at that. And basically what it does still confirm to us that as the deal valuation increases, the total deal equity goes down, right? The total deal equity goes down, or there's a negative relationship between those two variables. So that gives us some exposure, but the main takeaways with this module is that you want to be mindful of the fact that, first off, we want to understand what variables we have and the types, right? Are they categorical or numeric? And then along those lines, when we look at the test, do we actually have to use a variation of the parametric test, or do we need to use a non-parametric test because we're in violation of some assumptions? So that ends module 8 for us.